Module 5. MLC Configuration and Visualization. In this module, we will use MEMS Studio to generate a machine learning model with data captured from the ISPU DUX S12 accelerometer. We will then program the Nucleo F401RE and the X-Nucleo IKS4A1 expansion board with the generated MLC model and visualize the output of the model in real time. Finally, we will use the built-in automatic filter and feature selection to have MEMS Studio pick out the features of interest to generate a new MLC model to compare to our manually generated model. Click the play button at the top left of the sidebar. This will enable the sensors and start streaming the data from the board to the tool. Now select the Advanced Features tab on the left. A new menu pane will open with advanced features that are available for ST sensors, such as the pedometer, finite state machine, and machine learning core, or MLC. We will be evaluating the machine learning core, so select this option. Then set the workspace to use for our evaluation by clicking Browse at the top right. Then navigate to the /MEMS_Studio-Workshop directory. Then open the Module 5 folder. Then open the MLC folder. Click Select Folder. Since we are generating a model based off the ISPU DUX S12 accelerometer, be sure to select this sensor in the Sensor drop-down menu. In the Data Patterns to Load subpanel, click Browse. Then navigate to the /MEMS_Studio-Workshop directory. Then open the Module 4 folder. Then open the Processed folder. It is possible to select either one file or multiple files at the same time. Select all the files that contain the stable tag. There should be 3 files with this tag. Open these files. This will load the files into the file list. Set the data class label to Stable, then click Load. Next, click the Browse button again. Then navigate to the /MEMS_Studio-Workshop directory. Then open the Module 4 folder. Then open the Processed folder. And open the file with the Movement tag. Set the class label to Movement, then click Load. Finally, click the Browse button again. Then navigate to the /MEMS_Studio-Workshop directory. Then open the Module 4 folder. Then open the Processed folder. And open the file with the Shaking tag. Set the class label to Shaking, then click Load. The bottom subpanel should show all 5 files, with the first 3 patterns representing the stable class, the next pattern representing the movement class, and the final pattern representing the shaking class. Now we are ready to generate the attribute relation file format, or ARFF, file. This file is used to store data in machine learning applications. It contains a list of instances, where each instance represents a single window of data processed by the MLC. Click on the ARFF Generation tab at the bottom. We will set the Machine Learning Core ODR to 100 Hz to match the accelerometer acquisition rate, with a window length of 200 corresponding to 2 seconds of data. In the Inputs subpanel, make sure that accelerometer_only is set as the input, and that the full scale and ODR are the same as our data acquisition from the previous module, 16 Gs and 100 Hz. For the Filters subpanel, leave the drop-down box selection as No Filter Selected. Finally, we will select our feature of interest in order to classify our data. The data can be classified by various features, such as the mean, variance, energy, peak to peak, zero crossing, etc. If you recall from the previous module, one defining feature of each class was that the stable class had very little to no peak to peak variations. The movement class had slow, minimal peak to peak transitions. Finally, the shaking class had large peak to peak transitions, occurring very frequently. As such, scroll down in the list of features to peak underscore to underscore peak and enable the ACC underscore V2 feature. This is selected as we do not distinguish between movements in any particular direction, only in the threshold of the transition. Now click the Generate ARFF File button to generate and save the ARFF file to the workshop directory. It should automatically be named features.arff. This file will be used by MEMS Studio to generate the decision tree. At the bottom of the window, select Decision Tree Generation. Make sure that 1 is selected for the number of decision trees, as we are only determining between 3 non-overlapping classes. When multiple decision trees are created, these parameters can be independently set for each tree. These settings are further described if you click on the question mark at the top right of the subpanel. Click on the Generate Decision Tree button. This will generate a file with the decision tree based off the input data and the features of interest. The results are displayed, including the classification accuracy, how many separate instances were identified, how many of these instances were correctly classified, and how many instances were incorrectly classified. Now we will generate the configuration file to load into the sensor. Click on Config Generation at the bottom bar. We can customize the decision tree output values. We will leave these at their defaults of 0 for stable, 4 for movement, and 8 for shake. The end counter values are used to control the output, such that the instance must be detected a specified number of times before the output of the MLC is set. We will also leave these as 0, so that we get a change in output as soon as the motion classification state changes. Click on Generate Config File. A file named mlc.json will be created in the workshop directory, which can be loaded into the sensor. Click the Load Config into Sensor button to inject this into the LIS2 DUX S12. Once the request has completed, click on the Decision Tree Output Viewer button at the bottom of the window. The legend at the top shows the output of up to 4 potential decision trees. We have only used one decision tree, so focus on the output of dec_tree_out_1. This value represents the output of the MLC after detecting the movement class. The host application can read this value to take action. With the board flat on the table, the line corresponding to this decision tree should be at 0. Now, slowly pick up the board and leave it in your hand. The value of the decision tree should settle at 4. Finally, shake the board vigorously. The decision tree output should now be at 8. There may be additional transitions depending on how roughly you handle the board. We can evaluate the response of the model to various conditions. Now, we will generate a new model using the built-in automatic filter and feature selection functionality of MEMS Studio. At the bottom bar, select Access Tool. Here, the previously applied settings of the machine learning core, ODR, and window length, as well as the input parameters, should already be set. In the subpanel on the right titled Automatic Filter and Feature Selection, AFS, ensure that only the following boxes are checked: window length and features. We can uncheck the filters and exhaustive filter search parameters since we will not be filtering the input data. Expand the Expert Mode parameters. You can either manually select the parameters or choose a specific mode. These settings are further described when you click on the question mark next to the expansion caret. Take some time to read through the descriptions, then click X to close the Help window. We will leave the mode at Default, which will use ANOVA, ADA, Random Forest, and RFE. Set the maximum number of features at 15. Then click on Run. MEMS Studio will now analyze the data and determine an appropriate window length and features of interest. The analysis may take some time, so please be patient. Once the analysis is complete, we can view the findings. Since we have disabled the filter search, no filters should be selected. Scroll through the list of detected features of interest. In this video, we can see that peak-to-peak for each individual axis was detected as a feature of interest, in addition to other features. Click on the Apply to Settings button to apply the automatically determined window length and features to your ARFF generation. Now, click on the ARFF generation button at the bottom of the window. The window length and features will have been updated with those found in the previous panel. Click on Generate ARFF file to update the features.arff file with the new parameters. Click on Decision Tree Generation. Keeping all settings the same, click on Generate Decision Tree. This will generate a new tree based off the updated features. Click on Config Generation at the bottom bar. We will keep these settings the same as our previous selections as well. Click on Generate Config File. Then click on Load Config into Sensor. Click on Decision Tree Output Viewer. You will see the same graph as previously. The line corresponding to deck_tree_out_1 is the line of interest. Test various conditions, such as leaving the board statically on the table, holding the board in your hand, and shaking the board. Click the Stop button at the top left to disable data acquisition. Then, click the Connect menu item. Click Disconnect to discontinue communication between the board and MEMS Studio. Disconnect the USB cable connecting the Nucleo F401 board from your PC. Then reconnect the USB cable to reset the sensor's internal registers to their default values to prepare for the next module. In this module, we used MEMS Studio to generate a machine learning model with data captured from the LIS2 DUX S12 accelerometer. We programmed the Nucleo F401RE and the X-Nucleo IKS 4A1 expansion board with the generated MLC model to visualize the output of the model in real time. Finally, we generated a new model using the built-in automatic filter and feature selection to compare to our manually generated model. This concludes Module 5.